Hello and welcome to Talk of Today, where we explore developments in science, technology, and society, and what they could mean for the future. I'm your host, Sam Barton. This episode is another dive into what is one of the most fascinating and promising fields of our age, complexity science. It's a relatively new field that is transforming how we see and understand the world across multiple disciplines. Most importantly, it can provide us with a deeper understanding of our collective interactions with the complex biophysical system we call Earth, and how we might avert the catastrophes that loom. Joining me today is Professor Karoline Wiesner, Professor of Complexity Science at the University of Potsdam in Germany, and Associate Editor for the journals Entropy and Advances in Complex Systems. Her research focuses on the use of information theory in the study of formation, maintenance, and stability of complex systems. She is also one of the authors of the recently released book, What is a Complex System?, which served as the basis of my interview with her. In our conversation, we cover what is a complex system, what is complexity and what are some ways we can measure it, why information theory and complexity science are such powerful tools for understanding the world. We also spend a bit of time discussing entropy, order, and disorder, as well as a bit on how these things might be related to ethical value, which has been a bit of a pet interest of mine over the past few years. And without further ado, please enjoy my conversation with Professor Karoline Wiesner. Well, Karoline, I'm very excited to have you here. I'd love to hear how, before we really kick off the discussion, I'd love to hear how you came to be interested in information theory and complex systems. Like, what's been your intellectual track or journey that's led to you investigating complex systems and exploring the world through the lens of information?
It started with complexity. I got interested in it, but really by accident. I got a book as a present for my 18th birthday, and it was the history of the Santa Fe Institute. And I read it, and I thought, oh, that sounds really cool. And then I went off and continued studying physics and did a PhD in molecular physics. And then when it came closer to the end of my PhD, where I wanted to stay in academia and was thinking, so what should I actually do? I didn't feel that molecular physics might be my field. And I remembered this book again. I mean, it's a bit of a silly story, but this is how it happened. And I thought to myself...
What was it? What's the name of the book?
It's Waldrop's book. And the title, I read it in German, where the title is Isles in Chaos, and the English title is probably something with chaos. I mean, it's quite a well-known book by Mitchell Waldrop, I think is his full name. And I wanted to know whether this institute that he was describing still existed, and it did. And I saw they had a summer school. I applied for the summer school. I was accepted, and that was the beginning of a journey I'm still on. So I received a postdoc stipend from a Swedish foundation who just believed in me changing field completely, and told me, why don't you just go ahead and try it out. And I was welcomed by Jim Crutchfield at the Santa Fe Institute as a postdoc, and he brought me on the track of information theory, because he does a lot of that. So that's how information theory got in that research. Became part of my research interests. That's.
Mm-hmm. And how long ago was that? Because how long have you been in the space for?
So it's now 2021, and I started my postdoc in 2004. So that makes it 16 years, I guess. 17 years.
Yeah. So it's still quite early days. At least in my mind, it was still quite early days. I feel like a lot has happened. I hadn't even heard of complexity until 5 or 6 years ago. In the scientific way of framing it, I just thought of complex things as complicated things to something that's difficult to apprehend or understand. And now over the past few years, that word has just completely changed in meaning.
It's an interesting question. Why? I'm not sure, but you're right. The Santa Fe Institute was founded in 1984, I believe, and I was accepted into the summer school when it wasn't that well known yet, and now it's so well known. They're completely changed the whole enterprise, because, as you say, it has received so much attention, the topic per se, and the institute as a result. I don't know why that is, really.
Yeah, and thank goodness for it, because I feel like there's never been a more important time for, widespread understanding and adoption of, widespread understanding of how complex systems, what they are, how they function, and how much we don't know about them. And I guess just this awareness is really important given the stage where we're in today, but maybe we can come to that sort of stuff towards the end of this conversation. So I'd love to just talk to you about information in general, because I've covered it a few times in different ways with guests in the past, and I've always said it's this thing that we all have this intuitive awareness of, but we can't really point at it. It's not very easy to just say, to explain what information is. At least in my mind, we say we take in information and we process it. So how do you think about information? What do you think it is? What do you think it is not? And what misconceptions do you think people have of it?
Information, the term itself is being used in so many different contexts, and the understanding of information is different in these different contexts. So I like the quote. I believe it's by Bates, and information is the thing that makes a difference. And that makes sense in our everyday life. We receive something or perceive something as information if it changes something, right? It changes our knowledge, it changes our perception of something. And so that's a very everyday understanding of what information is, and that could be words, it could be events, it could be pretty much anything that enters our reality. But it already suggests something, or a way to understand it in a more mathematical way, which has its own way of understanding information. And there, information is, in a way, anything that's not random. You could argue. So information, if you translate it from the everyday understanding, is something conditional, right? Given my current state of knowledge, or given my current, my current reality, what comes in is unexpected, or is unexpected, unknown, unpredicted, that it comes in. And so already you have something that has to do with probabilities, and information has a lot to do with probabilities, and the mathematical definition of it is a function of probabilities. So the difficulty is that in the everyday understanding we have this we have context. Context is always there, and if I tell somebody, I don't know, I'm canceling our meeting today, then that's a piece of information, but it comes with a lot of context, right? It could be we had a fight the day before, so I'm canceling the meeting, and that's a clear message of, look, I don't want to see you anymore. But if it might have a very trivial reason. It's because you have a doctor's appointment. So there's context always around information, and that makes it so difficult to align mathematical ideas of information with the everyday understanding of information, because mathematically, at least in the original Shannon information sense, there is no context, or rather, everything that is relevant for the system is part of your computation of your probabilities, and they're not conditional on what day it is or what color your T-shirt is. and that makes it very hard. That's the current topic of research. How do you bring in the context? Because clearly, especially when we talk about complex systems, context seems to be so important. Right? If you want to quantify the information, say that a cell has when it makes a decision on moving or not moving, on traversing a cell, a membrane or not, then there is a context there, and the probability framework so far doesn't really capture that. I'm not sure. I might be going a bit off topic here, but what I'm trying to say is there are two understandings of information. One is very basic. It is a function of a conditional probability, or just a probability, depending on the problem. And the other one is, the difference that makes a difference.
I like that, the difference that makes a difference. I don't know if I've heard that, but
that's the Bates and quote.
It's kind of one of those tongue-in-cheek ways of responding. You're like, what is information? Oh, well, it's a difference that makes a difference.
But it captures it so nicely.
You're telling someone something without really telling them anything. But, it makes sense. Yeah.
I think you're telling them exactly what the problem is. No?
This... So, does all information... Like, in my mind, all information requires a material substrate for it to exist. You can't have information devoid of matter, right?
So that would be...
Or, I don't know. I think you've done a bit of work on quantum information theory, so perhaps that's completely wrong. But, like, my layman's understanding is that information needs to be based in some form of material construction, some organization of matter.
So certainly the transmission of information and storage of information, both, are ultimately relying on some physical space, right? So you can't have transmission of information. I mean, our speaking here is reliant on, transmitting of pressure waves through air, and then comes the whole digital communication and so on. But that's all based on physics, and equally, storage of information is ultimately a physical problem. I absolutely agree. And whether it's then quantum substrates or classical physics based substrates makes it makes a difference. Yeah.
Mm-hmm. So you mentioned Shannon. Like, what's Shannon entropy or Shannon information? What are you saying when you're speaking about information in this way?
Yeah, it is. So Claude Shannon was an engineer, and he published a famous piece of work in the 40s that's still now at the core of the research field, which is called information theory. And he introduced a function which is a function of a probability distribution. And he wanted to quantify the information content of an event, let's say. So he started out by saying, okay, I have a range of possible events here. And these events, because he comes from an engineering background, are signals that he might or might not receive. And he wanted to assign an information content to any possible signal that he might receive. Now that, of course, means he has already defined the set of possible signals he could receive. Right? So already we run into problems when we want to translate that into a complex system where we might not know what could happen, let alone what will happen. But in this framework, we do know what could happen, and then we assign probabilities to things that could happen, and then information content of an event that actually does happen is effectively the logarithm of its inverse probability. So that means the smaller the probability of a signal coming in, the bigger the information content. Okay, so if I tell you that Queen Elizabeth has well, let's take the recent example of Prince Philip. Prince Philip has died. Well, we didn't know when it would happen. We presumed it would happen, in the near future, given that he's 99. He was 99 years old. So the probability of it happening was quite high. The news content was therefore much lower than if we talk about a 30-year-old person, let's say, died. So it's a very it's a very clear idea of what information means. The more unexpected, the higher the information content. And so that's translated into this function where every event is being assigned this logarithm of its inverse probability. We take the average, and then we have the average information of this set of possible things that could happen. So an information is like a negative... well, information is like surprise, the average surprise. And if you have a set of events where just one of them is very likely going to happen, and then that's actually happening, the surprise is very low, and the information content of that event and equally of the entire set of possible events is very low. That is the Shannon entropy. And that's now at the heart of all the digital communication that we're using, because all of coding theory of communication technology is based on that function, Shannon entropy. And there is a legend that he didn't quite know what to call this function, and he asked, according to this legend, he asked John von Neumann what he should call it. And von Neumann said, "Oh, call it entropy. Nobody knows what it is. That's a great name." So he called it entropy. I don't know if it's true, but it's a nice story. And I mean, the connection...
There is more of a connection between... there is more of a connection between entropy, like thermodynamic entropy, and information entropy, rather than being things that are kind of hard to understand as well, right? Like, are they... I think I could be completely off here, but is Shannon entropy just negative thermodynamic entropy?
It's... So, first of all, you're absolutely right. There is more than an anecdotal connection between the two. In fact, the mathematical form of the Shannon entropy is identical, except for a multiplicative constant, to the Gibbs entropy. So the thermodynamic or statistical mechanical entropy, and it's still discussed why that actually is. Why should physics be, if a physical law, which statistical mechanics leads us to thermodynamics, leads us to the basic laws of thermodynamics, why should that be the same as an entropy that has to do with communication and probability distributions? And the answer, I think Penrose gives in his book, The Road to Reality, gives a very nice answer. No, it's a different book, but it's Penrose. A very nice answer to that. It gets us all the way into phase space and points in phase space of a physical system.
Anyway, so as we were saying, there is that connection between thermodynamic entropy and Shannon entropy.
Yes. So that connection is, like I was saying, is deeper than just an anecdote. And it has to do with the probabilistic nature of physics, really. And it's quite funky that we can describe physics. We can derive basic statistical mechanical functions from this Shannon entropy just by assuming, or by starting out with our own ignorance. And you might wonder, why would our own ignorance have anything to do with the physical law? But in this case, it works. And so by assuming, for example, all we know about a system is its average energy, from there we can derive the basic Boltzmann function of statistical mechanics as the most likely distribution of events, to use the language I've used before, in that physical system. So the Shannon entropy in that sense is really powerful because it captures, we use the word surprise information, but it captures the possible events in a physical system, and it tells us which ones are more likely than others, and we can do the physical experiment, and it works. So what's surprising about it is that there is this, it measures the ignorance about a system, but then if you turn it around, it's not our own ignorance really that is relevant here. I mean, that's totally irrelevant for the physics of something. But what's relevant is the number of possibilities that there are for states, for the physical system to take. And if we are able to enumerate these states and we're able to give them probabilities, we actually can find out in which state the system will be with high probability. So that's how it works. Why our own ignorance, which is really it's really a representation of the possibilities that the system has for its own behavior. And the Shannon entropy captures that because we maximize the surprise, and that means we maximize this function. But why that is relevant for physics is because it tells us what's the most likely thing to happen, and then we can do the experiment, and it works. We find the same probabilities again in the experiment.
So, to make sure that I'm sort of understanding here, a state is like a state is like the positions and velocities of every single particle in a system. Like that's one state, and all of there could be a hell of a huge number of states that a system can take, and they all have relative degrees of probability that there's a varying likelihood that these could be encountered, right? And the lower the chance of encountering it, the more surprising it would be to find that system in that certain state. So like walking down the beach, there's lots of sand, but then a sandcastle. That's a particular arrangement of matter that's far more surprising than just sand. A pile of sand, and Shannon entropy measures is a measurement of how surprising that state, how surprising that arrangement of matter is.
Correct, and the powerful thing is if we wanted to, link it to complex systems, is that what you said is right. So in physics, very often we would talk about positions and momenta of particles in which gives us a phase space. But equally, we could talk about very different events, like the the voting behavior of people, or the roaming behavior of a certain animal species, and equally, the Shannon entropy helps us to build a model of these systems that is guaranteed to include everything we know about the system, but not more, which is always is very important. You're not putting in assumptions that are not really needed to reproduce the data that you have, and that's why I like information theory, because you can use these. You can use it both in physics and beyond, and because it's based on probabilities, and probabilities rule the world.
Yeah, it seems to be the most versatile science in a way, the most versatile toolkit you could have in your toolbox, because you can apply it everywhere. At least that's what it seems like. Regardless of the discipline. Information theory can be applied and done in a way that's fruitful.
Agreed. Again, you run into problems in two ways. One is information theory is very data hungry, and physics is a beautiful subject because we've been doing it for centuries, if you like, and we know how to get data, and a lot of them. But in other areas, that's not the case. So, say, you're measuring gene expression of a stem cell. You don't get that many data, so you have to learn how to handle sparse data, and that's when information theory is, well, it quickly can run into problems because you can't specify well enough, say, the value of an entropy. And of course, the other limitation that it has is that it is explicitly excluding context and meaning, and that's a challenge.
Yeah, this idea of context and meaning. I want to ask you about order, and like order in the, like, it's got many different definitions, and I was thinking about coming to this later, but I think this is a good time to come into it. We say a system is ordered, or our society is in order, or there's disorder. We have these intuitive notions of order, and they kind of all have similarities. Like there is some overarching theme that ties them together. Like you could order something in terms of size, or some variable, some quantity or whatever. You can, like, if things are in a state of order, perhaps if like your washing machine is out of order, it will not operate in a way that is predicted of it. So there's like this thing that there's this thread that the word order weaves between lots of different, I guess, circumstances, and that it's generally the idea that things will happen in a way that's predictable, right? And it kind of fits into this idea of minimizing, or in this idea of surprise, or information. But I feel that, like, I've done a little bit of reading, and even in the book, What is a Complex System, there wasn't as much to do with order as I was kind of hoping for, just because, and I see it as it could be a part of this problem with the importance of meaning and context, because to say that a society is ordered, like how do we think of order? How, the way I generally think of it is, it's some sort of, and this is like one half of a definition, it's like a spatio-temporal territory where action will likely have its intended consequences, and there won't be any like surprising perceptual things going on, right? Like that's kind of how I feel about it. But I feel that the reason why I want to talk about order is it's this word that's so central to a lot of what we discuss. What is entropy? A measure of disorder, at least in thermodynamics. And we say complex systems are ordered, like we are ordered beings in some sense. So there's this word that's really being used a lot, and I'm just really trying to get a better grip on what it is from a more of a perhaps a scientific sense, like or an information theoretic sense. Like if we were to think about order in terms of information theory, what sort of answers would we get?
The term something being out of order is interesting, isn't it, in the English language? Indeed.
Yeah.
Now, the information theoretic answer for order is a lack of entropy. So zero entropy states are perfectly ordered. But what does that exactly mean? Mm-hmm. It means, again, what you have done is you have defined what events can happen and what probabilities do they have. Well, no, what events can happen, and then you look for their probabilities. And if it turns out only one of them is even possible to occur, all others have probability 0, you have, per definition, a zero entropy, and you have a perfectly ordered state. So what you've done then is you have decided what are the possible states of my system and what is their likelihood of happening. So I can try to translate that to the washing machine, right? So you have, every day you have a possible state of your washing machine, and the probability of it breaking down is, when you have it new, you would hope that that's a zero probability. So you keep on going day after day after day after day, confirming. It's almost, well, let's not get into Bayesian probabilities here, but every day you confirm, indeed, the probability of it breaking down is super low. I haven't seen that happening a single time. And then one day it does break down. So an event that you had in your own book of probabilities, you had it listed as probability 0 or tiny. It's happening, and first of all, it means the entropy has suddenly gone up, because something that's not accurate. What it means is an unlikely event has happened. So the event itself happening has a high information content, and that's that. The average information might still be low, so the entropy doesn't necessarily increase. And how does that relate to order? So in your spatiotemporal view that you mentioned.
Yeah, I'm thinking like, this law and order, we have social order. Like we live in this world where things happen as we expect them to. And I'm trying to think about, I'm thinking about order in these terms. Yeah.
Yeah. We can bring in the term stochasticity or randomness, right? So something that's perfectly ordered, we would say, doesn't have any stochasticity. So it doesn't have, everything is deterministic, everything is determined. So, if you go out onto the street, you will not be mugged. That's deterministic, okay, and you can rely on it. That's 100%. It's going to be the case. That's order. We perceive that as order, and we would hope that to be true for the place we live in. That kind of order is desirable. But there are places in the world, for sure, where this probability is not 100%, but it might be something like 50. Right? Half of the time you get mugged, and half of the time you don't. That's disorder. It's one way to think about disorder. Maybe that's closer to what you have in mind in terms of social order. But certainly the unpredictability is something that we perceive as disorder, right? Whether it is in a spatial configuration, or whether it is more in time, which we're mostly thinking about in everyday life, what's going to happen. And then if things are unpredictable, we perceive them as disordered. And that is, you could, in principle, quantify that with information and entropy. So these would be high entropy societies.
The disordered societies would be high entropy. Yeah. Perhaps this is something we'll come to later, like how do we even attempt to quantify these things? Like, I know that there's many, many, many different ways, and there's so many different ways. It's kind of daunting even trying to look into each of them. All right, so thank you for explaining that to me, indulging me there. Let's move on to, I guess, complex systems. I guess perhaps briefly, if you could just give me like a 2-minute summary for those who perhaps aren't as well versed in what a complex system is or what complexity science is. What is a complex system, and what does complexity science? What does it try to do?
I'll start with the first question. What is a complex system? 1 minute, 30 seconds. We think of a complex system as something that consists of many parts, and these parts have many interactions. And out of these interactions emerges something which individual parts cannot exhibit. So a standard example is an ant colony, where a single ant is, it doesn't have any intelligence. It would just go in a circle and die probably pretty quickly. But you put thousands of them together and you get a society with rules, with roles, with the ability to build bridges, to find food networks and so on. So we have, out of very simple components, something emerges which is not simple because it has, structure, it has order, it has it has maybe modularity, function. So all these things that we perceive as complex are coming out of interactions between many and usually simple parts. That's the brief on what a complex system is, and they range all the way from physics to social systems and things that are created by social systems like the internet. And then what does complexity sorry.
Yeah, I was just going to say, most of the examples of complex systems I hear discussed are things related to life, right? So it could be, a living organism, or the societies or the groups in which they exist, the ecosystems that they're a part of. But what are some examples of non-living complex systems?
Nice question. The boundary between life and non-life is a grey zone, of course, but we certainly, if we go to physics, an example of a complex system is the planetary and etc. Structure of the universe, where the individual parts, you could say, are pieces of matter, and they have arranged into fantastic structures of obviously the solar system that we're in, all the other solar systems and other structures like galaxies and so on, that are now having their own rules, which are then studied by astronomers and cosmologists. So that's an example of a complex system which is not alive. Of course, it contains life because there's life on Earth and so on, but the structures themselves are not living. Mm-hmm. So that would be an example. And then you could go to chemistry, of course, where you have self-assembling structures, and fabulous experiments where people show how molecules are self-assembling to very intricate structures without somebody taking a pincette and putting them into place. So that's chemistry, of course, biochemistry as well.
I think I remember reading in the book that there are maybe the necessary but not sufficient, sufficient but not necessary. I can't remember, but I'm thinking about adaptability, adaptation, like the ability to change behavior in response to something. Is that necessary for a complex system? And if so, how would we say that a galaxy adapts? A molecule, or how can these inert non-living systems be said to adapt? I just could be off here, so if so, please just let me know.
You're not off. Adaptability is a very central concept in the study of complex systems. It is a concept, though, that is related to something that has a function, and life is one example of systems that have a function. That's how we think about them and study them. So adaptability is certainly not a necessary condition. One can probably argue it's a sufficient condition for something to show adaptive behavior. It requires it to be a complex system. I think I'm pretty sure that that's the case. Mm-hmm. But it's not a feature of systems that are not alive or non-functional. We wouldn't talk about adaptability. We would, we would talk about self-organization probably. But adaptability presumes a functionality.
Mm-hmm. Okay, great. All right, so we've just briefly touched on complex systems and things that are, what are they? Examples of them. So you'd think it would be kind of self-explanatory what complexity science would do then, it's the study of complex systems. But at the same time, when I first came across it, it kind of, the way I perceived it was a new way of doing science. It's more than just like throwing, biology or chemistry or physics or all these other sciences in there. To me, it seems like a different way of, if this is like the conventional way, reductive, developing hypotheses and testing them, and just basically observing things, observing the phenomena in action. I feel like complexity science, when I first came across it, it really seemed like it was distinct from, or a big addition to, science, the way that we've done science over the past few years. Not in a way that it replaces it, or that it's like, I wouldn't say it's actually distinct from, but it's just kind of like there's new stuff that there's new tools that we can add into our toolbox, guys. Let's get to it.
Maybe I can ask back, what is it that made you think this is new, this seems different?
That's a good question. I just never really thought about things in these terms, and I think maybe the agent-based modeling. Like, how can you just look at something? How can you just plug things into a computer and hit play, and then how can that tell you about something that's that maps onto the physical reality? That it's analogical in a way. Something's going on in silica, that's completely separate from what's going on in the real world, and it's impossible to perfectly model a lot of these systems because, if you were to perfectly model it, you would have the system, right? You can't do it perfectly. So how do you go from having that as a legitimate, how can that be a legitimate representation of what's actually going on? How can that be considered scientific in the same way if you're running these experiments? Perhaps, economics, like, it might be a good example. Like, how can we say that if we're observing it in this computer model, it's connected to what's going on in the real world? I think just, reading about that, I think the first book that really brought it to my attention was Eric Beinhocker's Origins of Wealth. I think that was like I'd seen a few talks or a few lectures, I've had a few conversations, but it was that book that really just kind of, it was like going from Windows 95 to Windows 10,
Yeah.
In terms of my operating system, the way I saw the world.
It's a great book, Beinhocker's Origin of Wealth. Now, I think it's worth remembering that, well, certainly it's worth emphasizing that complexity science is not a new science in the sense we're not following the very important basic rules of science, which is we need to be predictive. What we produce needs to be explanatory to the world that we're observing, and it has to be confirmed. We have to be able to confirm it with experiments. Okay. So it sounds all exciting, and I have an idea of why it sounded exciting and new. But the reason is not that that we're doing science in any different way. But we're following the same very important basic ethics, if you like, of doing science. And one reason that it seemed new, and it was new in a sense, is the increasing availability of computational power and the resulting availability of data. So I think it's no coincidence that complexity science really took off at the same time when computational power really took off. And that's about in the 90s. And it has been increasing ever since.
There's one thing that I'd add, and I think this is really why I got really excited about it. Now that I'm thinking about it, I'm not very good at being I can't do one thing. I'm physically incapable of just being interested in one thing. So when I found out that there was this science, this discipline that kind of gave you access to a whole world of things, like it seems to be the discipline for the generalist, right? Same with information theory. You can just learn these two things, and suddenly, you're like a Swiss Army knife. You can just be thrown into any sort of situation, and chances are the principles that you learn will have some, level of applicability.
Yeah, I'm a bit like you. I love going from learning something about stem cells and then learning something about Twitter, and and just 1 week has gone by between the two. So it's a great, it's just great. And the reason that it seemed exciting, I think, lies exactly in that, or let's say the novelty underlies this observation, which is that because of the computational power, we're now able to take mathematical descriptions of one system and check them with a totally different system. And the reason is that we now have similar amounts and quality of data for people behavior, for example, online, because everything is digitized. And we have all these new technologies on, say, single cell spectroscopy that we didn't have a few decades ago. So this wealth of data that we're used to in physics is now rising in other areas of science, plus the increased computational power. So we can now throw all these data onto a computer, and we can, for example, you mentioned agent-based models. So we can now put such a model on a computer that relatively realistically simulates, say, a marketplace. And the the attractiveness of these models is I can come up with some simple rules, and I can check whether these rules have anything remotely to do with what I observe in the real world. So it might not be very deep, but it wasn't possible in the 80s to do that. And now it is. And so this availability of computational power allows us to translate many of the insights and also the tools that we have from physics, like phase transitions, or even thinking about a phase space of financial agents. It's possible now because we can simulate it on a computer, where we couldn't do that 30 years ago.
Mm-hmm.
And that's the exciting bit, that we can now in a quantitative way, step into fields that we couldn't before.
So there are these complex systems everywhere, and they exist at various different scales. Like, cells are complex, ant colonies are complex, our brains are complex, and we are all, we are nested. Our brains are in our bodies, and we are within societies. And we've got the little economies, we've got the global economy. So there's this nested, like all these little complex systems are nested within one another. Can you have a complex system at a higher level? So let's say the economy or something that's at that level, that is a lot less complex than its underlying modular, like its underlying components?
The short answer is yes. Often you see the phrase complexity from simplicity, which is what I've explained in the beginning. You have very simple parts, you put them together, and whoa, you get something much more complicated. But the opposite is true as well, which allows us to, for example, do computational social science. We have, a person is a very complicated and certainly a very complex system. But once we put a lot of people together, suddenly we get predictability again. You ask a psychologist, and they would have told you that decades ago, that groups are easier to predict than individuals, right? And that's exactly what we have with people, with animals. You predicting a shoal of fish or a flock of birds, and you can do that with relatively simple assumptions and very simple mathematical models capture quite a realistic behavior of these entities. And I guess for a lot of people, surprising insight is that we can ignore so many things. We can ignore the age of the birds. We can ignore, what they've eaten in the morning. We can ignore tons of things, and the behavior is still predictable. And that's probably also what gave this exciting feeling in the when complexity science really took off. It was that there is a predictability, although we are dealing with this complexity. but it's not complex in the sense of unpredictable. Oh my God, what should we do? We don't understand a thing. It's complex, and it makes it predictable. That's exciting, and that's what complexity science is doing. Is it's extracting those things that are relevant to give a prediction in the case where it's possible, and it's possible surprisingly often with very, very different systems. Mm. It's the kind of universalities that we.
So how would we like? I'm just going to ask you about. So, what array of tools or methods do we have to measure complexity? And I know that there's quite a number, so perhaps like the broader categories of them, or maybe just like the top 3 or 4. And when would you use one versus the other? And like, what are the benefits of or detriments of them?
Measures of complexities is my pet project. There's a whole chapter on it in the book, and the reason I spent quite a bit of time on it is when I started out, there were a lot of measures of complexity. Well, certainly a handful or more, and at some point I started to realize that they can give me a number of how complex something is, but surely they can't give me an idea of all the different aspects of the way in which a system is complex. I mean, we've talked about self-organization, we've talked about adaptation, we've talked about maybe clustered structures, and there are many other things. Disorder, we've talked about that. So surely I can't capture all of these things in one number. That would be nonsensical. And yet it's what's being done. And it's being done not because people are silly, but because without mentioning it, they're interested in a particular aspect of a system. So let's say economic complexity is something that has gained attention in the last years. And there are measures of economic complexity. And they're interested in particular aspects of complexity. And in this case, they're interested in the, if you like, the complicatedness of a product. So that would be something like the nestedness of a product. Is it simple? Do you just have to dig it out of the ground? Or are there many steps involved in making it?
Is it the ratio? It's like the ratio of inputs to outputs. Is that sort of like the measure of economic complexity? Like how much needs to go in to produce something at the end? I know that in Australia we are like terrible on the measure of economic complexity. We're like 110 or something because we're just like, we just a lot of our economy is digging stuff out of the ground and taking it elsewhere for it to be processed. I think I need to stop bad-mouthing Australia because every time I do, I think it just, the internet suffers.
Yes, but you're right. I'm not an expert on economic complexity, but that's roughly how it works.
Yeah. So we've got economic complexity, but there's a whole variety of others. What sort of ones are more, you could say, general, or if we had to, pick 5, we're going on a journey, and we need to pick 5 of our complexity measurement tools, and it's a desert island, so we can't have too many. We got to be, quite economical with our choices. Some of these things are quite heavy. Which ones do we pick? It's a terrible analogy, so I apologize.
It's a great question. My dream is being on BBC's Desert Island Discs show. That's when you've made it, and they ask you, what would you take to an island? So, right. The one measure or the one feature of complex systems that's, I think, always relevant to measure is order. It came up in our conversation several times now. I think that's no coincidence. Order, structure, and we've talked about self-organization. there are many measures of complexity that call themselves measures of complexity, but really what they measure is order in different ways, by using information theory or by using statistical tools. And the reason is that, order per se doesn't say anything about whether something is complex, because I can look at a checkerboard, it's perfectly ordered, but the checkerboard is, somebody painted the checkerboard pattern on it. It's not a complex system. But order is the result of self-organization. So if we know a little bit about the system and we think it is, or we know it is self-organizing, then measuring the order is a measure of how complex it is, how much order can it actually produce. So that would be the first tool I would put in my tool bag.
For the measurement of order, we were just talking about the movement of crowds. How these complex systems at higher levels, while their constituent elements might be incredibly complex, their behavior that they exhibit at that level won't be too complex. Would order in this sense be a good measurement there, or like at least not thermodynamic entropy? Because I guess you just kind of need to ignore what's going on underneath and then just focus on that relevant scale. Would you still use some measurement of? I guess my question is, how do you model a system? Like, if you think of them as each person as a particle, you can just get rid of all the underlying complexity. That's bingo. That word's just being said a little bit too much, I feel. But you can just kind of just ignore everything that's underneath and then model this system as individual parts. Would entropy still be a decent measure here? At least in the thermo, I guess you wouldn't use the thermodynamic sense, you'd just use the information sense. I don't know if you can see where my confusion or my question's coming from, but I'm not really explaining it too well. But I feel like you need to just ignore the stuff that's underneath, and that still might be contained within the measure in some way.
Let me see if I understand what you're saying. First of all, entropy wouldn't be a measure of order. You have to tweak it to make it into a measure of order, which you can. But it by itself is a measure of disorder. Okay. And order is always a relation between at least two things, right? So is one predictable from the other? That could be in time, in space. So you need a relation in order to talk about order. And entropy, you don't need relations. You can just talk about an ensemble of things, and how they relate to each other is not necessarily part of the measure. So you can use entropy to measure disorder. And then your question, I think, relates to the fact that we have two levels in a complex system, always. And usually we have more than two, but we have at least two. On the bottom level, we have the many elements that are interacting. And on the top level, we have the emerging order. Okay. So what we could measure is, on the lower level, we could measure the disorder, for example, in, say, molecular motion. And on the top level, we could measure the structure that arises from, say, the movement of animals or molecules or whatever it might be. So one is a prerequisite, or one is describing the conditions, and one is describing the outcome. I'm not sure I'm answering your question though. Yeah,
no. I think that gets it. That gets it. All right. Apologies for the interruptions and the clarifying questions. I just have just some little questions that have been in the back of my mind for a while, and I don't quite, I haven't quite answered them, at least to myself.
They're good questions,
okay.
So keep asking them. It helps.
I'm glad. So measurements of order is one way. Is one of the, if we were to, maybe we can bundle those together and say measurements of order is one of the desert island complexity measures. Yeah,
and I've just made a distinction between measure of order and measure of disorder. So I would need both. So that my second tool is the measure of disorder. And
yeah. Okay, so that's I guess they're not one and the same. I always thought you could kind of if I always thought that, they would kind of be the same thing, because, if something's ordered, it is less disordered. And if something's disordered, it's less ordered. I always thought that they'd be interchangeable.
So yes and no, I agree. The lack of order is disorder. Let me see if I can explain why I need both. I think the reason. So you're right in the sense that if I have a measure of order and it is zero, then there is disorder. Why I said I need both is the going from one level to the next. So if I think about the disorder of individual parts, I want to measure that. And then if I think about the order of the which arises from the interactions, then I want to measure. So I can have both in the system, right? So I can have disorder on the level of individual behavior, and at the same time I can and usually do have a measure of order, or a certain quantity of order, amount of order on this collective level. And now mathematically I can. I'm just thinking, can I dispose of one of them mathematically? Well, they're related functions. If I have one, I can bake the other. So yes, I think you caught me out here.
Yeah, well, I'm not trying to catch anyone out. I really wanted to make sure that I understand these things, because, I think I've seen this on Twitter as well, that, it's one of those things where you can read and learn so much and still feel like you don't quite get it. That's been my experience. Like perhaps just because it's kind of it's multidisciplinary, and I don't have a mathematical background, so I think I don't when I see all the probabilities and the when I'm reading and I see all these equations, I'm like, I only get it in terms of words. So perhaps that might be holding me back. But I've seen other people express their inability to really quite grok or grasp this space, this field. So apologies to you and perhaps the listeners who are listening now who get it, but I really just need to make sure that I'm understanding these things.
Well, your question is great, because I too see a lot of confusion in that respect, and this the statement of complex systems are between order and disorder, right? And I think that is a confusion between because we're interested in two different things here. The disorder is at the level of the constituent parts, whether that's people's behavior or molecules or whatever. And every complex system has a certain amount of disorder on that level. You look at a beehive and there will be masses of disorder, right, visible to the eye. And then at the level of, say, collective behavior, or at the level of molecular structure, you see order arising. And so the system, in that sense, is not between order and disorder. It has disorder in it, and that's required to maintain, to maintain its functionality, to maintain its complexity. And the order is an emergent phenomenon that arises from the disorder. So we're talking about the two different levels here, and that's why I distinguish the two measurements. Although mathematically, one function can be derived from the other. So,
yeah. Okay, great. That clears it up a bit. So we've done our exploration of order and disorder. I think we could put that aside for quantifying complexity. What other measurements do we have?
Right. So if I'm allowed some more tools in my toolbox.
Yes.
The phenomenon of I give it the general term non-linearity, and that is, if you want to think about it strictly, it's another phenomenon of order, or another occurrence of order, and what it is it expresses the fact that the whole is more than the sum of its parts. Okay. So I want to be able to measure non-linearity, and I can do that in several ways. So one example of of non-linearity is what has gained a lot of attraction in recent years is behaviors of people in cities. A city is a complex system, and yet we find it's full of people, millions of people, and you'd say that's totally unpredictable what's happening in a city. But it turns out that there are predictable elements in a city, and an example is crime rate. Right? You'd think you take a small city, you have a certain crime rate in that city, you multiply the number of people in a city by 10, the crime rate increases by 10, but it doesn't. It increases by more than 10. Other things go the other way around. So, or a fun example is walking speed of people. You'd say, well, somebody in a small town has a certain walking speed. You go into a big town, why should that change? But it does. It becomes faster. So I would need to be able to measure non-linearities.
Can't you predict the size of a city from the... Sorry to interrupt. Hasn't some work been done showing that you can predict the size of a city by just measuring the walking speed of its the citizens?
If the relationship is not too noisy, then that should be possible. Yeah, I didn't know that specific work, but I can imagine that. Okay,
I could. I trust. Yeah, I think I read it in Jeffrey West's scale.
Yeah. Mm-hmm.
Anyway.
Yeah. So non-linearity. This is one form of non-linearity, and the tools aren't complicated. I would just fit. Often people fit power laws, although they rarely exist in nature, but they're often helpful in describing statistical relationships between data. So that would be my third tool.
Mm-hmm. Yeah. So is that that is a measure of complexity in a way? Like you can find like the non-linearity of a system, and that gives you an indication of how complex it is.
So here I think we're entering a gray zone, because the hallmark of complexity is the existence of such non-linearities. Now, is something more complex than something else if the non-linearity is higher? Yeah, you could argue that. I haven't seen a convincing case where we would really compare two systems in that way, but because there's such a broad spectrum of possible models we could make. One is we model the relationship as a power law, but there are other options. So it's hard to compare, to take that measure in order to compare two systems. We could ask why we want to do that, and then maybe it makes sense. Which I think is the problem with all of these measures. I think I remember
reading in the book that perhaps there's... Oh, sorry. What was that? You think it's the problem that...
It's the problem with all of these measures is, what do you do with them, right? Why do you want a measure of complexity? And I don't know. I really have to think about good reasons or good examples of what do you then do with this. Of course, we want to be able to compare systems, but because complexity is something that lives in this high-dimensional space, if you like, it's hard to compare things with each other. I think it's more relevant
Yeah.
when you want to predict things.
So one of the reasons why I'm really interested in one of the reasons why I'm really interested in, well, I think complexity science can actually do a lot for our ethical reasoning. You know, like we are a species with finite resources, and for better or for worse, we are now stewards of the planet. You know, we need to kind of ensure that this planet works, and that, you know, ideally biodiversity increases, and that we don't move into a hotter house Earth scenario. And, you know, there's lots of things which we need to avoid, and hopefully make better. And I think complexity science can really help us identify perhaps what are the characteristics of systems that like have value. I mean, we have our intuitions, but I think complexity science and, you know, science in general this century might actually give us an understanding about what the material correlates for ethical value might be. And then if that's verified to some degree, it may enable us to triage decisions, right? Let's just say in some hypothetical scenario that we have to decide between saving 2 rainforests. You know, I know it sounds silly, but one of them is going to die. And they are different in some sense. Perhaps one is more complex, or, you know, has greater biodiversity. I don't really know. I think that these tools, these ways of seeing systems, I think what they'll be able to do is really empower us to make, I guess, normative judgments, like judgments about what we should be doing, not just from you know, if we take this action, this other action is likely to occur. More than, well, the characteristics of this system are such that it appears to have a great deal of complexity across multiple measures, and therefore it might be more ethically valuable, not only at this moment in time, but because systems of that nature are also more likely to beget greater complexity in the future, right? And I think, you know, there's like some instrumental, the fact that we can take advantage of that in the future, in some sense, also may give it some greater level of value. I don't know if that made much sense, but if there's anything I need to clarify, just let me know.
I think it made sense. I'm not sure I would agree with you. It sounds like you're suggesting that, you know, assuming we can measure the complexity of these rainforests and compare them in that sense, which I think is very difficult. But if we assume that, then you're suggesting that the rainforest that's more complex on that scale is the one that we should rescue, and the other one we should let go. And I'm not sure what's the justification for that.
I'm not sure about scale. Yeah, I'm not sure about, well, the justification. Yeah, I don't know about the term scale there, because, you know, that's where things get a bit messy. You know, they might not be very, very complex, but it might have very important constituent elements. You know, the constituent elements might be highly sentient beings, you know, like ourselves, or, you know, primates or whatever. I guess what I'm saying is that it appears to me that the things that have, and we're sort of digressing here, but the things that we deem to have that are more morally valuable, like we think whales are more valuable than insects, so we think, you know, dolphins are more valuable than I don't know, perhaps cats. And I think, and, you know, humans are obviously very, very valuable. At least that's what our intuitions tell us. Anyways. And while that, yeah, exactly. So while our intuitions are anthropocentric, they are biased. I think that there is some mapping on between what we perceive as valuable and, like, complexity, or them being highly ordered systems or things. And I think there's like a correlation there. And I think that, I mean, I guess that's yet to be determined, but I think that, I feel like that's the case. And we could do some experimental philosophy here, you know, just survey a whole bunch of people about what they think is valuable, and see what the corresponding complexity measures or entropy measures are. Whether or not we can actually do that is another question. And then kind of see what the data says. But there's obviously a lot of underlying assumptions here. However, I do think that this perspective could actually provide us with some answers. Because I don't think sentience is enough. Like, a lot of the utilitarians, they think that what is important is the experience of sentient beings, and the more sentient beings that are experiencing good things, the better, right? The greatest good for the greatest number. But I don't think that's sufficient, because sentient beings need to be they are embedded within systems, and they require they require sustenance, they require energy to maintain social order, and they need to be embedded in, at least on Earth, we need to be embedded within the biosphere for our oxygen and for our food and all of that. So you can't just think about sentient beings, you need to think about this system entirely. And I think that this way of seeing the world, complexity science, order, all these wonderful things that we've been talking about, can kind of help shed some light on this area. I sort of derailed us, but I just thought I'd just clarify what I was saying.
So if I can comment on it, I don't think you derailed us. I think you're on a slippery slope, and to get us off that slippery slope, it might help to specify what the aim is, right? So if we're comparing to rainforest and we're wondering which one should we save, we must ask for what purpose, okay? And then we might be able to give an answer. And if we're deciding between insects and whales, we should ask, what's the purpose? What goal are we trying to achieve? And we might find that insects are actually much more important to keep our ecosystem going than whales are, right? So our maybe the everyday intuition and biases towards something as impressive as a whale will not get us very far. But complexity science has something to offer here, and that is precisely that. So I'm not an ecologist, but there's lots of work there where an ecosystem is considered, and all the species in it, including plants and flora and fauna, and it's asking for the functioning of that ecosystem in its current form, which elements are key. So there's this notion of key species, and then you've clarified a clear goal. We want to keep the ecosystem functioning as it currently is. What is relevant? So taking out a certain species, does it, in this model and given the data that we have and the understanding, does it matter? And then we can say yes or no or maybe. And that's a much more well-defined question than asking, what's more important or what's more interesting, an insect or a whale.
I agree with that entirely. I think that's what our intuition sort of maps onto. And if we were to take in this absurd hypothetical world, if we just had to choose between two organisms devoid of any context, which one would be another, then perhaps we could use that as a way of doing it. But that'll never happen. I'm thinking about it more in a probabilistic sense, what action will ensure that there's continuity of the good, you could say, the ecosystem, and will likely lead to greater flourishing, right? So, and that you can think about that in terms of complexity, greater biodiversity, a net decrease in local entropy, right? I think that's kind of the trajectory that we're on, and it kind of corresponds, for us to live good lives. You and I, we can have this conversation through the internet across the world and collaborate. We can get lots of food. We can do all these amazing things because we have access to energy. We have access to a ridiculous amount of energy compared to our ancestors.
But Sam,
and all of that is dependent upon.
I think I need to interrupt because I don't understand even what you mean by flourishing, by lowering the local entropy. I've lost you there, or you've lost me.
Okay. Yeah, that's good because you know more about this than me, so you can really highlight some holes in my thinking. This is so flourishing is kind of you can think of it as the ultimate state of well-being, right? if you were as good as everything in your life was as good as it really could be, that'd be like the peak. That'd be like the best things could be.
For me.
And
But that
there's
might
obviously
not be
the
the
inverse
best
for you, but there's
for
also
others.
for others. Yes. But if we could try to, if there's like some way that we could just maximize that number for all of life, for all of sentient things, like this is kind of what the utilitarians want. Like that's what they think we should be doing, right? Like that's like that moral frame. That's how we should be. That's what, like, the consequences of our actions. That's what we should be thinking about when we make ethical decisions. And what is most relevant is like the experience of sentient beings. That's like one frame. So that's what I kind of mean by flourishing, like just the experience of the good by as many people as possible, right? And I think that is dependent upon increasing order in the world, because our well-being is sort of dependent upon us being within social systems that are ordered, so that we can get adequate nutrition, so that we can get enough sleep, we can have our vaccines, we can there's this whole array of things that fit into our subjective well-being that are dependent upon our ability to act in the world in a way where our actions will generally have the desired consequences, and things won't, result in disaster, right? So I think, like, would you say that our society today is far more ordered than it was, 1,000 years ago? Like, even if we were to take it from like a thermodynamic, or information theoretic sense of entropy, would you say that things are a lot more ordered now than they were before, or a lot less disordered?
I think that it is not that simple. I don't think I can actually make a statement about that. Right? I mean, I certainly can say that. I can talk about crime rates, and I can see that they're going down. I can talk about death rates through war. I can see that they're coming down. I mean, people just have to. Pinker likes to talk about these things. That the world has gotten a lot better in that sense. Mm-hmm. Is it more ordered? I'm not sure. At the same time, we're now, because the planet is it's populated by 3 times as many people as it was 60 years ago. We're facing problems like these pandemics like the one we have at the moment. So does that mean? Well, I don't even know how to start talking about things are more ordered. The world is becoming more and more connected, and that means both people are being more and more connected, but also the social, ecological, economic system the systems are being more and more connected into a single social, ecological, economic system. And that's, I don't know if it's more ordered or not. It's certainly bigger.
Yeah. I mean, we could definitely say that, like, if we take into account biodiversity loss, or just the destruction of the environment, I think we could probably say that it's a lot less ordered than it probably was way back when, or 100, 200 years ago, because we've really taken over this planet and have destroyed a lot of things. I was thinking more from it's hard to, everything's kind of connected, so if you try to put these artificial boundaries to try to talk about the system, and I was kind of referring to our social system, like our societies, rather than the totality, like rather than like the biophysical system of Earth. But yeah, it's I get the impression. So I remember reading one rough metric. I think it might have been alluded to in the book. I can't remember, but energy rate density, like the amount of energy running through a system per unit time, per unit mass, and that being is like a proxy for complexity in a way, because complex systems obviously require energy to maintain their form across time, and the more complex something is, or the higher the scale, the more energy is required, I guess, to maintain that system. And energy rate density could be a good, I guess, a proxy for that. It could be a good proxy, not a definite measure, but just like a proxy for it.
I think it's similar to saying that the size of the system is a proxy for its complexity, and that in some cases that works, and in other cases it doesn't, right? So we're going back between complexity and order, and complexity, like I say, is multifaceted. So the size of the system might very well be an indicator of how complex it is, and energy consumption is a proxy for size. But then if you go back and ask, well, how much self-organization is happening in that system, how much functionality is in that system, then it might turn out that the bigger system is less complex than the smaller one. That's difficult. But if I come back to order, then we can be much more precise. It's much easier to talk about order. And we talked about that in the beginning, that this, if we take Shannon entropy as a measure of order, or its absence, its lack as a measure of disorder, and its lack as a measure of order, we need to first of all specify all the possibilities that we think a system has in its behavior, or in its let's stick to behavior, which narrows down, or which specifies much more what question are you really asking when you say, has society got more ordered? Well, you need to specify first which behaviors you're interested in. Are you interested in criminal versus non-criminal behavior? Are you interested in economic investment in 10 different portfolios? What are you interested in? And then we can give a measure of order. But it's relative to the parameters that you're interested in. And I think it's important, because to say, I don't know, humanity flourishes, what are we including in this system that flourishes? Are we including insects or not? Is our flourishing somehow related to insects or not? And if we're excluding it, then we get one value. If we're including it, we will get another. So we have to specify in relation to what. And it's the same with this Shannon entropy. It's usually not stated explicitly, but it is there as a prerequisite. You first have to define what the relevant parameters are. Is it people, or is it something else?
Yeah, I mean, just intuitively, I think all of it, if possible, like not just people, but like the whole of life. I think something that one of the mistakes I've been making in this discussion is kind of confusing, like, if we think of like, this is just all the different scales, I'm kind of taking all of this into totality, whereas you have different levels, and each level can have varying degrees of complexity. And I think that, and levels of, I guess, like the way I think about it is, if there's a system up here that's got all these parts underneath, that system would have like a measurement. Sorry, for those listening, I'm pointing at my arm, and there's like a scale, going down to up. The top of the scale is the higher level, and the lower scale is the lower level.
Is that in terms of the size of the system?
Of,
so on your arm, the upper part is bigger systems, and then the lower you go into zooming in.
Yeah. So space? This would be like, So this would kind of be the global economy, and then this would be. The global economy's got lots of people, and those people have organs, and those organs have cells, and those cells, I take that in totality. Like I'm thinking about like summing all that together in some sense, and giving it a number, giving it some term, right? And I'm confusing that with the complexity that's going on at each of the levels. And I think that's that's caused some confusion in my own head, but also in this conversation as well, because I've been kind of, like, sometimes I think I've been conflating them.
Well, they are connected, right? So first of all, there is, often one reason for the need for a measure of complexity that's given is that we want to know, does the complexity in the universe increase or not? as the universe is expanding. And we don't have an answer really, but we could give individual answers by, say, the number of species that have come into existence in the last millions of years. That's more specific. And so you could ask on each individual level. You could talk about complexity, like you're saying, is how complex is on the level of microorganisms. If you take them as individual parts, what kinds of structure do they generate? And then that is your universe that you're studying with the tools of complexity science, for example. But you can of course also ask about the number of levels in the system. If you start with the economy and then you go all the way down to quarks, many levels that you're passing through here. And I mean, making probably quite a few assumptions, you get a number. I don't know what that number is good for, but maybe it is good for something.
Yeah. I just feel like that's something that separates all of them. That there is some number there. I just the way I see it is like it's some level of order. Like that's the way I kind of conceive of it. Perhaps wrongly.
Well, it's confirmed by time, isn't it? Evolution. I mean, evolution started out with fewer levels, and then once humans came into the picture, and then we've added some more levels in terms of the systems that we've invented, like the economy. So it's not that silly to say that levels have been added over time.
So we're nearing I'd say the end of our time allotted for this discussion. I know you've got to get some lunch as well. So I guess one or two questions to wrap up. And I guess one of the questions I was going to ask is, what are some of the biggest misconceptions? But I think we might have covered that a bit, just given what are some of the biggest conceptions people have of complex systems? So other than the ones that I might have, voiced in this conversation, do you have any others to add, like in your conversations with people?
There is one that comes to mind. If it counts as misconception, you tell me, but there is a conflation, certainly, very, very regularly between complex systems and chaotic systems. So chaos in a mathematical sense, but it's quite intuitive, really. That is a system which is really a set of equations that are coupled differential equations, whatever, a set of equations that are describing the movement of something. And because of the nature of these equations, the movement is effectively unpredictable beyond a very short time window. That is often mentioned together with complexity. Complex systems are chaotic, but these are completely different phenomena, and there is a good reason, and it's more a historical reason, I think, why they're mentioned in the same sentence, which is both of these fields have gained they've gained a lot of momentum through the advent of computational power, because the predictability, or rather unpredictability, of chaotic systems has been, people could study it in much more detail once they could put it on a computer and run it for long times. And complexity is often considered to be, unpredictability is part of complexity, but then unpredictability is part of many different things as well. So that's not enough to connect chaos and complexity. They are two different phenomena.
Mm-hmm. And what lesson from, if you were to pick one lesson or one thing to keep in mind, one takeaway from complexity science that would help us best, perhaps individually, but perhaps more collectively navigate the times that we're in. So if there's one lesson that we could take away from complexity science to help us navigate the world more effectively, what do you think it would be from your mind?
It's a tough one. Two things come to mind. One is the one of the big insights is that we can translate knowledge from one field to another. So we can translate knowledge from, say, material science to epidemics, where the physics of these systems is totally different, and yet we can translate knowledge from one to the other. So that's what's helping, and that's related to the second insight, which is these universalities that we're seeing that make it possible to do complexity science. So it makes it possible to jump from one field to the other, and that's helping us to tackle new problems by looking back over our shoulder and using knowledge from previous, maybe completely different looking systems, and yet we can use the knowledge.
Yeah, it's very exciting. We get to just go and look at old questions with, a new set of glasses and see things in new ways. Very exciting. If people want to find out more about your work, if they want to keep up to, with your work, what you're up to, where would you direct people online? Obviously, there's your book, What is a Complex System, which I'll link on my website and in the show notes and all of that. But if people just want to keep up to date with some of your work, where would you direct them?
So there's my website, karowiesner.org, which I do my best to keep up to date. I'm not on Twitter, I'm afraid. So, but ResearchGate is something that people can sign up to. I'm medium traditional when it comes to means of dissemination.
It's probably a good thing. Helps you focus a bit more. Like Twitter is this wonderful and terrible place. I think it's the best of them, but it still has its problems.
I might just not be brave enough.
Yeah. Well, Karoline, thank you very much for taking the time to have a chat. I really enjoyed it.
Thank you very much, Sam. It's been a pleasure.
And actually, is there any request for the audience? Like, is there anything you'd like to say before we wrap up? Or, other than buy a book, which I think I definitely recommend. Any requests at all?
Requests for the audience?
Or parting messages, or, parting messages, requests. I guess you kind of covered it with your with your two things to keep in mind.
I think dialogue would be my request. Keep up the dialogue, and so for a complexity scientist, dialogue is part and parcel, because I can't possibly say anything sensible about, let's say, molecular biology without talking to a molecular biologist, because I'm not trained in it. And I think the same translates to any part of life. We need to keep up the dialogue with people who have knowledge that's different from our own, and then it's true for Twitter as well. Keep twittering, but Twitter to people who have other opinions than yourself.
Yeah, wonderful. Well, thank you very much.
Thank you, Sam. It's been a pleasure.